Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to discuss other norms for finite dimensional vectors. So in this topic, we will define the 1 norm and the infinity norm for finite dimensional vectors r to the n and c to the n. We will observe that these two norms continue to satisfy the properties of a norm as described in the previous topic on the 2 norm. We will then describe and explain the application of these two norms over, for example, the more usual 2 norm. Alright, if u is any vector in f to the n, f being either the reals or the complex, you'll recall that the 2 norm was defined as the square root of the sum of the squares of the absolute values of the entries. Now we'll define the 1 norm. The 1 norm, denoted with a subscript 1, is simply the sum of the absolute values of the entries. The infinity norm is the maximum of the absolute values of the entries. Alright, so consider the following 5-dimensional vector. Then, if I was to calculate the 2 norm, I would square each of the entries and add them up and take the square root of that result. Thus, we are calculating the square root of 2.56, which is 1.6. So the length of this vector is 1.6, according to the 2 norm. The 1 norm just adds the entries in absolute value. So in this case, we have a 1 norm of 3. Finally, the infinity norm is just the largest entry in absolute value, which in this case happens to be 1.3. Now, both of these norms satisfy the 3 properties that we saw of the 2 norm. For example, both the 1 norm and the infinity norm is greater than or equal to 0. After all, in the first case, we're just taking the sum of the absolute values of the entries. In the other, we're taking the maximum of the absolute values of the entries. So in either case, the value of the norm for any u must be greater than or equal to 0. But not only that, the 1 norm and the infinity norm are both 0 if and only if the vector u is 0. And that's clear. If any one entry of the vector was not 0, then the absolute value would be some value greater than 0. So therefore, the 1 norm would be greater than the absolute value of that one entry, and the maximum of all the entries would again be greater than or equal to that one non-zero entry. So therefore, the only way that the 1 norm or the infinity norm can be 0 is if all the entries are 0. Next, both the 1 and the infinity norms are absolutely scalable. If I was to multiply every single entry of a vector by alpha, then the 1 norm would become larger by a scale of the absolute value of alpha, and the maximum would become larger by a scaling of the absolute value of alpha. Finally, although it's a little bit more difficult to show, both the 1 norm and the infinity norm do satisfy the triangle inequality. Now, you will have to show some of these properties perhaps on an assignment. Now, why would an engineer want to use a different norm from the 2 norm? After all, the Euclidean norm is used very often by engineers and often for good theoretical reasons. However, in some cases, the 2 norm may actually be inappropriate. Suppose you're a tourist in New York, or perhaps you're authoring an app for a tourist in New York. You'd like to get from the entrance of the St. Patrick's Cathedral and you'd like to go to the entrance of the Museum of Modern Art. Which distance are you going to give? Are you going to give the distance as the bird flies, or would you give the distance as the fox runs? Well, of course, if you're writing this app for a tourist, the tourist is going to have to be following the streets. And so consequently, what distance do we want to give the tourist? Do we want to tell the tourist that the distance is 267 meters, that is the 2 norm, or do we want to give them that the distance is 382 meters, that is the 1 norm, the absolute value of the distance in one direction plus the absolute value of the distance in the second direction? Next, for using a different norm, let us consider moving the head of a 3D printer. In this case, the movement of the model or the head is controlled by 3 separate motors. One motor, in this case, moving the model in the X direction, the next motor moving the head in the Y direction, and finally the motor moving the head in the Z direction. Now, all 3 motors can be turned on at the same time, or you can turn on one motor at a time if you wish. If all 3 motors are on, the head is actually moving faster. So, in fact, the time it takes to get from one point U in R3 to a second point V in R3 actually depends on the infinity norm. It only depends on the maximum of the 3 distances, because that is the motor that will have to be left on the longest. Now, in this course, we will almost exclusively be using the 2 norm. However, there are scenarios, as I just described, where engineers will use other and more suitable norms. So, following this topic, you are now aware of the 1 and infinity norms. You understand that these norms also have properties similar to that of the 2 norm. And you are aware that there are applications where you would be using these norms over and above using a norm such as the 2 norm, or the Euclidean norm as you may have seen in secondary school. Here's the references, the acknowledgements, the colophon, and a disclaimer. Cheers!